On June 1, 1939, the T-class submarine Thetis is arguably among the Royal Navy's newest boats. She is about 270 feet of high tensile steel, designed to hunt in the deep ocean. On the surface, she displaces a little over 1,000 tons and substantially more when submerged. She is packed with the latest ASDIC and hydrophone gear, propulsion, and weaponry. But in the early afternoon, during her final acceptance trials in Liverpool Bay, this massive complex system is defeated by a single latent defect. Compounded by a procedural misread, the killer is not a torpedo or a mine. It is a plug of bitumastic enamel blocking the test cock so completely that it reports nothing. That tiny blockage triggers a catastrophic system reset. In marine engineering, we often focus on the large components like the pressure hull or the main diesels. But the chain of casualty usually begins at the smallest interface between the dry interior and the wet exterior. Thetis is running a dive trial. In the early afternoon, the first dive is attempted, and she fights her buoyancy, reluctant to settle. So the crew begins a survey of tanks and internal tubes, chasing trim with checklists and assumptions. The crew needs to flood the torpedo tubes to adjust trim, but they must verify the state of tube number 5. The protocol is mechanical and absolute. Before you open the rear door of a torpedo tube to load or inspect it, you must verify that the outer door, known as the bow cap, is shut. If the bow cap is open, the tube is an extension of the ocean. To check this, the engineer opens a small valve on the rear door called the test cock. If water sprays out, the tube is full and pressurized. If air comes out or nothing comes out, the tube is dry. On Thetis, the test cock on tube number 5 is opened. Nothing, no spray, no hiss. In checklist logic, that reads as dry. They unlock the rear door. The moment it is cracked, the inrush takes over. This is where the paint alters history. Prickers to clear the test cocks exist. They are on board, they are not used. During construction, a painter had applied the protective bitumastic enamel too thickly inside the test cock assembly. The viscous material had hardened, plugging the orifice completely. The tube was actually full of seawater, held back by an outer bow cap open to the sea. How it became open is not conclusively established. The port is blind, and they won't learn it until the rear door breaks its seal. When the rear door swings open, the physics of flooding takes over with violent immediacy. This is the concept of unconstrained ingress. We are not talking about a leak. We are talking about a 21-inch diameter column of solid water, driven by the pressure of the ocean, entering a compartment at high velocity. The equation governing this is derived from Bernoulli's principle, which dictates that as the pressure differential creates flow, the velocity of the water entering the ship is massive. Even at shallow depth, the water does not pour in. It jets in like a horizontal pile driver. It hits the bulkhead with enough kinetic energy to knock men off their feet and sweep heavy gear into the flood stream. The volume of water adds tons of weight to the bow in seconds. A submarine relies on neutral buoyancy, a delicate balance where weight equals displacement. The sudden addition of tons of water at the extreme forward end creates a massive moment arm. The bow is pulled down by gravity, overcoming the lift of the reserve buoyancy tanks. The crew attempts to close the watertight doors to the torpedo compartment. They manage to secure one, but the butterfly nuts on the other cannot be tightened fast enough against the onrushing chaotic flow. The compartment floods completely. The weight acts like an anchor chain dragging the nose down. Thetis pivots on her center of gravity. Her bow smashes into the seabed at about 160 feet. The impact is hard. The stern, still buoyant and filled with air, rises up. The bow is down on the seabed, the boat canted at an extreme angle, pinned by flooded forward spaces and bottom suction. The engineering reality is stark. The ship has not imploded. The pressure hull is intact. The power systems are offline, but the air bank is initially sufficient. However, the exit is blocked. The bow is buried. The angle makes movement inside the ship nearly impossible. Every loose object has fallen to the forward bulkheads. The casualty is now defined by a hard geometry. The ship is too heavy to surface on her own tanks. The water in the torpedo room cannot be pumped out because the bow cap is still open to the sea, meaning the ocean will replace any gallon pumped out instantly. The defect is sealed. The trap is set. 103 men are alive inside a steel bottle, waiting for a rescue that requires reversing the laws of physics that put them there. At 150 feet of depth, the window for survival is defined by a ruthless arithmetic. The seabed provides a hard floor, but the real ceiling is the limit of human physiology under pressure. After 4 men escape, 99 remain trapped inside. They are not drowning. They are waiting in a pocket of air that is slowly turning into poison. The clock is not ticking in minutes, it is ticking in partial pressures. During the rescue attempts on June 2nd, the stern is at times above the surface, exposed like a door left ajar. This creates a cruel illusion of safety. Inside the hull, the conditions are deteriorating rapidly. To get out, the crew must use the escape chamber. This is a steel airlock designed to flood, equalize with sea pressure, and allow men to exit using the Davis submerged escape apparatus. The device is a primitive rebreather. It scrubs carbon dioxide and provides oxygen. But the logistical bottleneck is severe. The chamber creates a throughput trap. It must be flooded, equalized, opened, and reset under pressure. Each cycle costs time the men do not have. There are over 100 men on board. The math is impossible. Woods and Oram are among the first to get out, carrying a message to the surface. Then the system is pushed harder. An attempt is made to force 4 men out at once. It fails, and 3 drown. One more 2-man escape succeeds, Arnold and Shaw, before the hatch jams. After that, there is no more throughput to force, only the sealed hull and the air turning against them. But inside the hull, the remaining 99 men are facing a quieter, invisible enemy. We must explain the concept of partial pressure and toxicity, which is the governing constraint of this chapter. In a sealed volume, humans consume oxygen and exhale carbon dioxide. On the surface, air contains only 0.04% carbon dioxide. If that level rises to 5%, it causes confusion and panic. But inside Thetis, the air pressure is rising due to the flooding in the bow, compressing the remaining atmosphere. Gas laws dictate that the physiological effect of a gas is determined by its partial pressure, not just its percentage. If the pressure inside the hull doubles, the toxicity of the carbon dioxide doubles, even if the percentage remains the same. The men are not just running out of air, they are being subjected to an accelerating chemical intoxication. They become lethargic. Their decision-making loops degrade. They begin to fall asleep, sliding into a coma from which they will not wake. On the surface, the rescue destroyers arrive. They see the stern, they can hear tapping on the hull. Some later described it as a kind of phantom telegraph. The rescuers believe the crew is signaling for help. They tap back. They hear more tapping. It reinforces the belief that the men are alert and waiting. In reality, the tapping is never confirmed as a deliberate signal. In tide and stress, rescuers cannot know what they are hearing. The rescuers are communicating with gravity, not with the crew. On the surface, commanders debate the unthinkable, cutting into the exposed after end to reach the men. But every option is a wager against the unknown, the risk of sudden flooding, structural uncertainty, the limits of tools on hand, and a sea that refuses to hold still. They fear that opening the hull could vent precious air and pull the stern down. They do not know what internal doors are shut, what spaces are already lost, or what bulkheads are still holding. This hesitation is fatal. Hours pass and the air inside grows heavier. Oxygen falling, carbon dioxide rising, judgment dulling under pressure. But accounts also point to a final, abrupt turning of the screw. A sudden shift of pressure and flooding around the escape system that may have ended the remaining lives in moments, not minutes. The silence inside is now final. The rescue mission is over. The salvage imperative begins. For a few desperate hours in the afternoon of June 2nd, the stern of the Thetis serves as a tombstone for the men dying inside. It projects out of the water at an angle of 35 degrees, a gray steel monolith rising nearly 20 feet into the air against the backdrop of a calm sea. The site creates a false sense of accessibility, tempting the rescuers into a battle of brute force against a lever arm they cannot possibly control. The immediate imperative is to prevent the submarine from sliding backward and disappearing completely into the dark water of Liverpool Bay. Tugs and salvage craft move in to execute a hasty stabilization plan. They do not have time for calculations. They pass a 3.5-inch wire rope around the exposed structure of the submarine, lashing it to the tugs to hold the attitude. This is combat engineering, where the variables are unknown and the materials are whatever is at hand. This operation fails because it ignores the fundamental physics of tensile failure in wire rope. A wire rope under load is not a solid bar. It is a complex machine made of twisted strands that store potential energy like a coil spring. When a salvage wire connects a floating ship to a sunken object, it becomes the transmission line for every wave, every swell, and every shift of the tide. The load path here is critical. The Thetis is not a static weight. She is a 1,000-ton pendulum pivoted on her nose in the mud. As the tide rises, the buoyancy of the tugs lifts them up, but the submarine is anchored by the flooded bow. The wire rope is caught in the middle of this vertical war. The tension rises violently under the wave-driven shock loading as the tugs heave in the swell. In engineering terms, every material has a yield point. Below this point, the steel stretches and returns to shape. Above this point, it enters the plastic deformation zone where it stretches permanently. Beyond that lies the ultimate tensile strength. When a wire rope hits this limit, it doesn't just separate, it parts, dumping stored energy in a fraction of a second and whipping the ends with lethal velocity. The salvage team is fighting a cruel material contrast. The entire disaster was initiated by critical fittings and door hardware, the alloy used for the torpedo-tube rear doors and bow caps. This material is chosen for its resistance to corrosion, not its ability to withstand the crushing impact of a bottoming. Now the rescuers are trying to save the ship using high carbon steel cables, but the geometry is wrong. The manganese bronze components failed due to a blockage. The steel cables will fail due to overload. The end comes with a violent snap. The 3.5-inch wire, taut as a piano string, exceeds its breaking strength. It parts with a sound like a gunshot. The tension vanishes instantly. Without the restraint of the wire, the buoyancy of the stern is insufficient to overcome the leverage of the flooded bow and the suction of the mud. The Thetis begins to slide, slowly at first, then gaining momentum. The gray steel stern slips beneath the surface. The water closes over the rudder and the hydroplanes. A marker buoy is thrown, but the physical connection to the 99 men inside is severed. The ocean has taken the hull back. The grab-and-hold phase is a total loss. The Navy realizes that simple tension is useless against a flooded submarine. They do not need to pull harder. They need to lift smarter. They need a machine designed to negotiate with the tides. How do you lift 1,090 tons of dead weight from the seabed without a massive crane? The answer is that you do not lift it. You force the moon and the ocean to lift it for you. The failure of the wire ropes in the initial rescue attempt proved that fighting the ocean with static tension is a losing battle. The Royal Navy shifts from a rescue footing to a heavy industrial salvage footing. Lift barges are brought in. And then the merchant ship Zelo is adapted for the job, fitted with heavy lifting beams and wire slings. The principle is still tidal lift. Set the gear and take the strain at low water, then let the rising tide add buoyancy to the lifting vessels and translate that rise into upward pull on the wreck. No crane wins this outright. The tide does, one lift at a time. This bypasses the problem of tensile shock that snapped the wires in the previous attempts. The load is applied gradually. As the buoyancy increases, it overcomes the suction of the mud holding the hull. The Thetis breaks free from the bottom. She is suspended in the water column hanging from the camels. The Zelo then tows the entire assembly toward the shore until the submarine grounds again in shallower water. The team waits for the next low tide to slacken the wires, shorten them, and repeat the cycle. It is a slow, walking process. Lift, move, ground, reset. There is a frantic urgency to this mechanical rhythm. The Admiralty is not just recovering a hull, they are hunting for a fatal flaw. They need to understand the rear door failure mode, and to fit a positive mechanical safeguard, later nicknamed the Thetis clip, so the same mistake cannot be repeated so easily. Until the Thetis is raised and the mechanism inspected, uncertainty hangs over every boat built to the same logic. Finally, after months of incremental lifts, the Thetis is worked inshore toward Anglesey. By early September, the wreck is brought into very shallow water off Moelfray, close enough that at low water she lies in roughly 15 feet. From there, she is brought into the shallows and ultimately beached at Traith Bychan, where the hull can be drained and examined. The physics of tidal lift have triumphed over the weight of the water, but the physical recovery brings the operation to its darkest psychological threshold. The ship is no longer a rescue target or a salvage challenge. It is a sealed crime scene containing 99 bodies. The technicians have defeated the ocean, but now they must open the hatch and enter the foul air of the interior to confront the reality of what happened in the dark. The interior is silent. After the mechanical triumph of the tidal lift, the salvage operation enters a phase of grim biology. The Thetis is beached and drained, but the atmosphere inside remains a toxic hazard, heavy with the byproducts of advanced decomposition. The salvage engineers must now don breathing apparatus not to dive, but to walk the dry decks of a ship that has become a mass grave. The recovery of the 99 bodies is a logistical operation carried out with somber precision. But parallel to the recovery of the crew is the recovery of the truth. The Admiralty investigators move into the torpedo stowage compartment to verify the physics of the disaster. They are looking for the smoking gun in the hardware. They find it at torpedo-tube number 5. The evidence is frozen in steel. The rear door of the tube hangs open. The bow cap, the outer door that guards against the ocean, is also found in the open position. This confirms the fatal sequence. The tube was a straight tunnel to the sea. The investigation confirms the presence of the bitumastic enamel blocking the test cock. The paint speck is real. The entire loss of a fleet unit and nearly 100 men is definitively traced back to a microscopic obstruction in a sensing line. With the forensic questions answered, the Royal Navy makes a cold, utilitarian decision. The hull of the Thetis is structurally sound. No depth collapse, no explosion, just a pressure tube that endured and a boat ruined by seawater. Aside from the water damage to the electrical systems and the soft furnishings, the steel tube is intact. In 1940, with the war in the Atlantic accelerating, the Admiralty cannot afford to scrap a 1,000-ton weapon system. The order is given to refurbish the ship. This process is exhaustive. The interior is stripped to the metal. Every wire, every gauge, and every valve is removed and replaced. The engines are overhauled. The torpedo tubes are scrubbed. The risk of galvanic corrosion, where dissimilar metals eat away at each other in the presence of seawater, is checked and mitigated. The ship is essentially rebuilt from the inside out. But a machine that has killed its entire crew carries a weight that engineering cannot scrub away. Among the submarine service, the vessel acquires the reputation of a coffin ship. Sailors are superstitious. They know the history of the steel they are standing in. To break the psychological link to the disaster, the Admiralty erases the name. The Thetis is struck from the Navy list. In her place, the submarine HMS Thunderbolt is commissioned. This is the definition of a successful salvage in wartime. The objective was not just to recover the dead, but to recover the asset. The tidal lift worked. The industrial refurbishment worked. Thunderbolt creates a paradox. She is a brand new ship with a ghost in the machine. She is assigned a new crew, men who must compartmentalize the knowledge that they are sleeping in the same bunks where 99 men suffocated. The technical pivot is complete. The ship that was pinned to the bottom of Liverpool Bay by a flooded bow is now fully operational, armed, and prowling the surface. She is deployed to the Mediterranean theater. The salvage engineers have done their job. They have cheated the seabed of its prize. But as Thunderbolt heads south to join the war against the Axis supply lines, she is moving from a hazard of accident to a hazard of intent. The ocean does not negotiate, and the Italian Navy is waiting. To understand the finality of the submarine's fate, we have to look at the water off Capo San Vito, Sicily, measured in thousands of feet, not hundreds. Down there, pressure climbs into the 4 figures in pounds per square inch. It is a domain that allows for no mistakes, and in 1943, no rescue. By March of 1943, the ship formerly known as Thetis has been operating as HMS Thunderbolt for over 2 years. She has exorcised the ghost of her first sinking through hard service in the Mediterranean. She has sunk enemy shipping and delivered commandos. The crew has learned to trust the hull that once killed 99 of their predecessors. But on the morning of March 14th, Thunderbolt attacks an Axis convoy and is counterattacked by Italian escorts, including the corvette Cicogna. Reports credit depth charges with sinking her, but the exact sequence and even the exact attacker is not conclusively established. What is certain is what follows. After the attack, the submarine is never heard from again. If the pressure hull failed at great depth, it would not have been a slow drowning. A deep hull collapse is sudden, a violent compression that leaves no time for rescue and almost no time for awareness. The Ciconia observes oil and debris rising to the surface. There is no tapping on the hull this time. There is no stern breaking the surface. The depth of 4,400 feet is an absolute barrier to salvage technology in 1943. The hull is taken a second time, into depth no one in 1943 can reach. The legacy of the Thetis is a paradox of engineering and tragedy. In 1939, she was lost because a layer of paint was too thick. In 1943, she was lost because the water was too deep. She remains one of the very few submarines to sink twice under the same steel identity. First in peacetime trials, with 4 men escaping, and then in war, with none. And despite decades of retelling, Thunderbolt's final resting place has not been conclusively located and identified in the deep. She is a war grave all the same, one that in her era could never be raised.